So to prove this, we note that tan has singularities at odd multiples of pi by 2. So therefore tan of pi z has singularities at the half integers. So this is a half, 3 halves, and so on. Minus a half, minus 3 halves, and so on. So now what we do is we have this is actually slightly simpler. We end up with, we choose a square contour where the corners are at n times 1 plus I. Okay, so this is so that's it lies on integers. It passes through integer points n and n times I. So again, we consider the contour integral of fz tan pi z. It's then straightforward to show in the same way as we did before that in the limit as n goes to infinity, this integral, this integral, this integral, this integral are all approach 0. So this is equal to 0. So that means the sum of the residues of all the poles inside are equal to 0. So if we work out what are the poles at places where fz doesn't have a pole, what do we end up with? So places where fz doesn't have a pole are where n does not equal zj minus a half and z equals a half integer. So we've got f of z, I'll write it as sine pi z over cos pi z, and I may as well put a pi out the front. No, okay, I'll leave it like that. And z equals n plus a half. Okay, so for any integer. So what does that give us? Well, we have a pole because of the cos term, simple pole. So using p over q dashed, we end up with f of n plus a half times, and then sine pi n plus a half, and then that's going to be divided by, when we differentiate cos, we'll also get a minus sign from differentiating cos, and we'll also get a factor of pi, but otherwise we'll get sine divided by sine. So basically we get the same as before, except we end up with a minus sign. So this is why we don't have a minus sign here. But otherwise, the working is the same as for the other case.